Hi everyone, welcome back to another workshop in the Explore Expander Bootcamp. Today we have Ryan Cowell from Tools for Humanity coming to give a workshop on privacy preserving machine learning. Hi Ryan, thanks for joining us.
Hello Rebecca, hello everyone. Wonderful to be back at Encode, and yeah.
When you're ready, feel free to share your screen and we'll jump right in.
Okay, that sounds good. Okay, so yes, hi everyone. As Rebecca mentioned, I'm Ryan from Tools for Humanity. I've been on Encode before, so I don't know, some of y'all might have seen me. Anyway, not important. But yes, in a previous life, I did a bunch of machine learning and deep learning research at Stanford. Did a bunch of vision research, not so much NLP, and afterwards got really into cryptography. Founded Modulus, which was this zkML company with my friend and co-founder Daniel, and we recently joined Tools for Humanity to become their applied research division. So here we are, still working on kind of zk and zkML related things, but yes, so I don't know. Okay. Cool. Okay, before I get started, could I get everyone to type into the chat what y'all's exposure and or background in kind of machine learning, deep learning, so on and so forth looks like? Purely that, sans all the ZK stuff that we will also touch on. So I do have my second laptop to my left, which is also in this Zoom or this room, which is excellent. But okay, then in that case, I will screen share. At any point, please feel free to ask questions in the questions channel or to just drop whatever in the chat. Yeah, and we should. 43 out of 5,000. Okay, sounds good. Yes, and I will address those as things come up. And Rebecca, also feel free to interrupt me at any time. Like zero knowledge, perfect. In case I miss a question. But okay, let's do this. So we are sharing screen. We are sharing the entire screen. And okay, awesome. Okay. I'm gonna wait for this to load. Okay, excellent. Okay, so hello everyone, welcome to the bootcamp for today. So the things that we will be talking about today, if time allows, are basically machine learning. So what is machine learning? What is deep learning? What is this thing that everyone has been so fascinated by and has generated so much hype basically recently? We'll also talk a little bit about machine learning and privacy preserving machine learning, or zkML, basically applying ZK proof techniques such as GKR, which if I understand correctly, y'all just learned about from Yupeng, to basically the field of machine learning or to machine learning models. We'll also dive a little bit into how basically GKR specifically as a zero knowledge proof system or as a proof system in general relates to machine learning. And then finally, we'll talk a little bit about the applications of zkML, or basically what zkML gets you such that you can build kind of cool things with it. Okay, excellent. So that is the game plan for today. And as mentioned earlier, please stop me at any point if you have any questions or are confused about anything or have corrections to anything that I have to say. That would be wonderful. But okay, without further ado, let's get started. So the first question is, what is machine learning? So machine learning, canonically, I guess we can talk about it more abstractly, and then we will dive more deeply into the form factor, which is deep learning, since they're similar, I would say, but deep learning uses some more specialized techniques, some more specialized architectures, and so on and so forth. So what is traditional machine learning? Well, I actually like to think of machine learning as just kind of like, you're almost like training, for example, like a human to recognize things. So let's say that here is Ryan. So here's me. So this is Ryan. And you who are an expert in the classification of various butterflies out in the wild would like to teach me, Ryan, how to be your lab assistant and to basically go out in the wild and to collect and sample butterflies. However, I don't know anything about butterflies. Like, all butterflies look like monarch butterflies to me. So if you gave me, a random butterfly picture, I cannot draw, so I'm very, very, very sorry about this. But if you gave me a random butterfly picture, then my output or my response is always going to be monarch, which is probably wrong. So this is how we're kind of starting out, right? Like, you have this uninitiated lab assistant and you really, really need to train me in doing this. So one way you could do this, of course, is to tell me like, okay, Ryan, monarch butterflies are the ones with, I think, orange spots and like black kind of like outlines and stuff all around. So here are kind of like the features of basically monarch butterflies, and that's how you're able to kind of recognize them versus a different kind. I literally don't know any other butterfly species, but you get the point. So that is one way you could do it. You could like handcraft, quote unquote, such features or such characteristics of butterflies so that I might have the ability to recognize them in the future. However, this is really time consuming on your end. Like you have to basically like tutor me in all this stuff. And you also need to like ask yourself, who are already an expert, like, okay, what are all the features of these butterflies that tip me off as to like what they are, right? Instead, what you would like to do is you would like to basically drop a giant dump of a bunch of butterfly photos in front of me and say, all right, Ryan, study these for the next month and then come back to me once you've basically figured out all of these things. And then in a month's time, I will say, yes, I've been diligently staring at butterfly photos for the past month. Now I think I'm able to classify almost anything you might throw at me, right? And so that, of course, is going to be much preferred because you can just print out a bunch of photos or just send me like a Dropbox link or something, and then I can just go through all of those on my own, and I will be able to just do that. So that is kind of the magic of machine learning, as I think about it at least, which is that traditionally when we want to teach our computer systems or even like our lab assistants or whatever things, right, we can try and like hard code things. We can try and basically say, okay, well, logically speaking or semantically speaking, all these things are true, so you should try and like think about things in this way. However, the entire field of machine learning basically said, nope, 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 nope. We don't care how you choose to learn it. We don't care what patterns you pick up or anything like that. All we care about is the fact that when you see a photo of X thing, you are able to tell me with 95% plus confidence that it is actually X thing. And whatever trends, whatever pattern, whatever thing you need to do to learn that, we don't really care. We'll hand you kind of like a learning algorithm, quote unquote, or like an objective function, exactly as Noah just said. But otherwise, you know, you will just go off on your own and basically do that. So that is kind of like the very high level intuition for machine learning. Okay, sorry, given this real quick, are there any questions? Going once? Going twice? Okay, no one's typing in chat. So we're gonna say sold question. Oh, okay, excellent. All right, cool. We're moving on. Okay, cool. So let's make this slightly more formal. So what do we mean by this whole like lab assistant and this like in the field and so on and so forth? Well, in traditional machine learning, there are two phases, and nowadays there are potentially more phases, but we can talk about that later if y'all are interested. TLDR, in traditional machine learning, there is the training phase, and then there is the test phase. Technically, there's also something called the validation phase. We can talk about this if you all have questions about it, but otherwise, the conceptual breakdown is that there's the training and the test phase. So what happens in the training phase? Well, the training phase is exactly when you took me, the lab assistant, and said, here is a million examples of basically different butterflies. So in this case, I, as the lab assistant, am the untrained machine learning model. In other words, I am a function, f of what I'm going to call x comma theta, which outputs something called y. And I guess if we define this, yeah, so in other words, what we're saying here is that x is going to be the input to this function. So in this case, that is the butterfly image. F is going to be the model or the model architecture, i.e. like just me as a human or how the model is structured. Theta is going to be what we call the learnable parameters. So this, I guess in a like neurological sense, you can think of this as, oh, Ryan is forming like new connections in his brain, right? Let's see. No, yes, that is exactly the right intuition. Yes, feeding data to learn, test is checking exactly how well it learned, slash actually deploying the model in production, because that is ultimately what you want to do, right? So theta are the learnable parameters. And then finally, y is going to be the model output. And just for today, we're going to be talking about classification models. So these are models which are trained on a task, which is basically a multiple choice test. So if we take the butterfly example, for example, you can think that if you are handing me a new butterfly image, then there's a list of maybe 100 different butterfly species, and I need to basically say, yes, I think it's species number 37, for example, or I think it's species number like 65, and that will be my answer to this test. So in particular, Y in this case for classification tasks is generally modeled as a one-hot vector. So it can look something like 0, 0, 1, 0, 0, in case I think, for example, that the third class or the third choice on the test is the correct one, or more canonically for machine learning, it'll look more like 0.05, 0, 0.95, 0, 0. So it'll generally be a discrete distribution that adds up to 1, as all distributions should do, which basically states how confident that model is in each of the answers or each of the predictions. Okay, so this is kind of the basic kind of like setup. And during training, what happens? Well, what happens is that you have something called the training data set. So this, which I'm going to call xi, yi, from say I equals 0 to let's say 1 million, 0, 0, 0. Okay, so this is going to be basically a set of pairs such that each of the yi's are the correct prediction for each of the xi's. So again, these will be the kind of like training like butterfly images, and then the y's will be the ground truth labels is what we usually call them. So the ground truth labels. Okay, and the whole idea during train time is that I will repeatedly ingest through the model all of the xi's. So for all of the xi's, basically I will compute f of xi, comma theta, and I'm going to make a prediction, which I'm going to call y hat. And so in this case, y hat may or may not be equal, question mark, to y, because I'm an untrained lab assistant, right? There's no way that I would just know these butterflies from the get-go. And so, it's very probable that, for example, y is something like 0, 0, 1, 0, 0, and then y hat is something like 0.2, 0.3, 0.3, that's 0.8 in total, 0.1, 0.1. Right, and so obviously this is not a good situation, right? Like I'm only 30% sure that the answer was what the answer should have been. So this is not great. However, this is where the training process actually comes in. Oh, thank you, C. I really appreciate it. This is where the training process comes in, right? So generally speaking, in machine learning, we will have something called an objective function or a loss function. So in this case, we can define, for example, L of y hat, comma y, as maybe something like y hat minus y quantity squared. So this is what we call like the square, or really, technically it should be 1/2 because we take the gradient, then the 2 goes in the front, so on and so forth. But point is, this loss function basically says, okay, well, the closer that y hat and y are to each other, the lower this loss is, right? The less regret we have about basically picking this y hat as the actual prediction. And so what happens during train time is that basically, and this is going to be a big hand wave, but basically for all of the parameters in your model, you're going to use a little bit of calculus here, and you're going to ask, well, what is partial theta, partial L, right? So what this tells you is if I change, if I change the parameters theta in this way, how does that affect the loss function? And of course, as we've seen here, you want to minimize the loss, right? Like you want y hat and y to be as close to each other as possible so that the model is actually predicting what it's supposed to on the train set. And so when you basically take the gradient of the parameters in your model with respect to the loss, you're asking, if I tweak this parameter, how does that tweak the final objective in the end? Therefore, I should update my parameters in a way such that I basically tweak the objective in the end to be minimized as much as possible. In other words, during training, what we do is we say theta gets updated to the old theta. So I'll call this theta new, should be theta old. And then it'll be minus alpha times, and then it should just be partial theta, partial L. So this is what we call the parameter update function. And the whole idea here is that partial theta, partial L is, you can think of it as like the direction of greatest increase in the loss function. So if I change theta in this way, it will increase L the most. And therefore, if I subtract partial theta, partial L, subject to this alpha, which is what we call the learning rate. So this is just a tunable parameter. It doesn't matter too much. But the point is that if we subtract the gradient from the old set of parameters to get the new set of parameters, the hope is that the new set of parameters does slightly better on this training set, right? Because we've taken a small step in the direction of reducing the loss function. Therefore, with the labels, the predicted labels should match the ground truth labels a little better. Okay. Okay, I realize that we actually dove pretty deep in the training process. This isn't totally necessary for the zkML part, but I just think it's pretty cool and interesting to get intuition. What questions do folks have right now? Just very, very, yeah. Okay, we'll give it a sec. Oh yes, Andrew Ng is, yes, he's quite a good teacher. I took CS229. That was a time. Cool. Okay, looks like no questions. Great. Okay, then let's talk about test time. Which just kidding. C is typing. We'll give C 1 sec. Oh, excellent. Okay, no questions. Great. Okay, so now let's talk real quick about the test time. So this is much more straightforward than training. Actually, okay, so the question is, well, what is the output of the training process? And the output of the training process should be a set of parameters, theta final, which basically are the result of the training process. So in other words, after I have iterated through my entire training set, so let me pull up the thing. Yeah, so I'm going to go through my entire training set. I'm going to do all of these predictions. I'm going to ask myself, hey, what is my loss for each of these predictions? And then I'm going to compute all of my gradients, and then I'm going to update all of my basically weights in this way, right? So if I do this process repeatedly and I go through my training process a ton of times, well, I'm going to keep on updating basically theta until I've gotten to a point where I'm pretty happy with the parameters. And so that is what theta final is. So theta final is the result of basically doing this training process a bunch of times. And now for all intents and purposes, it is fixed. So we are not changing theta final anymore. We're just going to deploy it in the field, in the wild. And this is going to be kind of like how things work. Okay, so during test time, what happens? Well, now that Ryan, the lab assistant, has actually looked through all these butterfly images, finally, you, the PI, can come to me and say, okay, hey, Ryan, here is this species of butterfly that I've not seen before. I know that you've seen this in your kind of like giant data set of stuff. Please tell me what this is, right? So what basically you, the PI, are asking me is, here is a new X, which is an example, quote unquote, from the wild. In other words, this is an example for which we don't have a label for, right? Because we are now trying to classify this or predict the label. And so now it's very, very straightforward. The entire inference process just looks like running f on x, comma, theta final. And we're going to call this, again, we'll just call this y hat. This will be the prediction, and this will be the actual thing that you use. So using a model in deployment, or what we call inference time, is literally just taking the parameters that you trained, feeding in some new input, and then getting whatever the output is from that and taking that as a ground truth. Cool. Okay. Okay, I assume probably no questions on the inference stuff. If y'all got the training stuff, that, yeah, the training stuff is much more complicated. Okay, excellent. Okay, so in general, this is the machine learning process. And in general, this is what I guess like folks have been doing for a long time before even deep learning. So now let's talk a little bit about deep learning. So we'll shift gears a little bit and talk about, okay, what is deep learning? What do the model architectures look like? How does it differ from machine learning, so on and so forth? Because that will be kind of like the focus of the rest of this. Cool. Okay, so part 2, deep learning, question mark. Okay, awesome. Okay, so deep learning is machine learning, but where F has a specific look to it, so to speak. Here's what I mean by that. So folks have probably seen the neural network diagrams that kind of look like this. These are a little bit old, I would say, at this point, because I am old in the machine learning community, and there's all these newfangled transformer things coming out. And so I hope folks still remember this. see, what do they look like now? Yeah, basically everything is a transformer. Even if you're doing vision stuff, it's just a transformer. However, transformers do have this kind of structure inside as a building block. So if y'all are interested, we can definitely talk about the architecture of a transformer. But why don't we focus on kind of like the canonic thing for now? Okay. Yes, exactly. Yes, no, you got it. Yes, this diagram is basically what we call a multi-layer perceptron or a fully connected neural network. And this is the one that we'll kind of focus on. Okay, so in this model, okay, so the first question is, why is it called deep learning? Well, learning refers to exactly the thing that we just talked about. There's this training process. You allow the model to basically learn its own parameters, and then you deploy it into the field. So there's no kind of like ambiguity there. Why is it called deep learning? Well, in deep learning, you have this model which basically has a bunch of layers in it. So if we look at this diagram here, well, there's kind of like three very obvious layers, right? So here is the input layer, for example. Here is what we're going to call hidden layer 1 or H1, and then here is going to be the output layer. And if y'all remember Yupeng's GKR lecture, this should look a little familiar because GKR circuits are also layered arithmetic circuits, just like deep learning models. And so the two have a very, very nice kind of like mesh in the middle. But yes, in general, this is how like the multi-layer perceptron works. Okay, so now let's ask ourselves, well, what do each of these lines mean, right? So importantly, every single basically input in this case is connected to every single thing in the hidden layer. And there is a line between the input and that hidden layer, between input and that hidden layer, between this input and this hidden layer, and the input and the last hidden layer. So what does that actually look like? Well, actually, it's a little easier to study it from the hidden layer's perspective as opposed to the input's perspective. In other words, I already know what the input to this model is, right? Because that is the thing that I'm feeding into the model. However, what I don't yet know is how to compute H1. So let's call this node H11, let's call this H12, H13, and H14. Cool. So the question is, what is the formula for H11? Well, let's just look at what connects into H11, right? So the things that connect into H11 are very easily, and let's call the input X1, X2, and X3, just so that we have some good notation. But yes, so X1 is connected to H11, X2 is also connected to H11, and X3 is also connected to H11. So in other words, H11 should equal some function f of X1, X2, and X3. And in particular, in a multi-layer perceptron, we basically have a linear function. So in other words, H11 is going to equal W11 X1 plus W12 X2 plus W13 X3. And usually there's also a bias term, but yeah, we can just keep that as well. Okay, so this is the this is the kind of notation for how H11 works. Oh, wow. Yes, backprop could be incoming though, but I think we might not get to backprop this time around because we do still need to talk about the ZK side of things. But thank you for your enthusiasm. I really appreciate it. Okay, awesome. Okay, great. So that's the formula for H11. And in general, actually, for any of the H1s, for H1i, the formula is very similar. So in other words, for H1i, this is just going to equal W1i X1 plus W2i, W1i, sorry. It is Wi1 rather, X1 plus Wi2, X2 plus Wi3, X3. Okay, okay, awesome. So, so my first question is, can anyone tell me, given this formula for H11, how would I convert this into a dot product between two vectors? If I could have someone type that in the chat. Or if you're not super sure, ask a question that would help you understand how. Okay. Right. Taking a moment. That is a lot of dots. No worries. Okay, maybe I'll give you all 30 more seconds. Okay, let's see. Na says weight matrix times input matrix transpose. Cool. Okay. I think that, yes, I think that is very close. I think you don't need to transpose the input matrix if it's on the right side, I think. But yeah, it's all kind of like very similar. Okay, so I guess maybe to write this out a little more specifically, h11 we can say equals the row vector w11, w12, w12, w13, b1 times the column vector x1, x2, x3, and the constant 1. And so if you remember basically how dot products work, you basically just zip the two lists. So you go w11 times x1 plus w12 times x2 plus w13 times x3 plus b1 times 1. Okay, so this is the TLDR behind how you get h11. Now, if we were to stack all of the h's together, right, h11, h12, h13, and we were to do the same thing, well, now all we have to do is, again, just put all of these basically weight vectors on the left side. So this would be w21, w22, w23, b2, and then w31, w32, w33, and b3. And again, each of these, based on the usual kind of like vector-vector product or vector dot product notation, would simply look like w21 times x1 plus w22 times x2 plus w23 times x3 plus b2 times 1. And then same thing for w31, so on and so forth. I'll just underline them for kicks, right? They're all being multiplied by the same vector. Well, this gives us exactly what Noah was talking about, which is that if we think about basically this h1 thing, oh, actually there's an h14, sorry. h14, you get the point. It's the same thing, dot, 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 times this vector. Okay, so if we think about then all the h's as also a vector, well then this entire operation just becomes a matrix vector product, right? So in other words, the vector h11 all the way to h14, sorry, this should just be the weight matrix, which is what Noah was talking about, which is just the collection of all the weights. So w11 all the way through b1, w21 all the way through b2, w31 all the way through b3, and then w41 all the way through b4, times the column vector x1, x2, x3, these are just going to be the inputs, and then 1. And so this is the sort of succinct linear algebra, quote unquote, way of representing a fully connected layer. Okay, what questions do y'all have so far? Okay, sounds like everyone's got it down pat. Okay, cool, cool, cool. Let me check the questions tab. Awesome, no questions. Okay, yes, please don't be shy. As in, if you're confused by this or have questions, please ask. This is quite complicated conceptually, so just let me know if you have questions. But okay, all right, then in that case, we will move on. So, okay, so now that we've basically discovered that this h11 through h14 equals this weight matrix times the inputs, I'm going to write this even more succinctly. So h1 I'm going to use to denote basically this vector. So in general, we're going to say that h1 is in R4. The weight matrix, we're going to call this W1, since it is the weight of basically this first kind of connection layer. And W1 in this case is going to be in R4 by 4. And then finally, the inputs here, which I'm going to call X is going to be in R4 as well. Technically, it's an R3 plus a 1 concatenated, so maybe we'll say that X is in R3, but you know it's in R4. Sorry. Yeah, okay, we'll just say it's in R4. That's chill. Okay. Okay, thank you, Hen. Yeah, just want to check in, not trying to lose anyone, so everyone needs to be on board. Okay, great. So now that we kind of denoted these things, the ultra succinct way of writing this is H1 equals W1X. And oh, I see. So I've incorporated the biases into the linear system. Sometimes you don't have to do this. So sometimes we can move the B's out and we can move this 1 out. And then in that case, we would say W1X plus B, where B is just that single vector, basically, that is the biases. Okay, excellent. So in general, when we talk about a multi-layer perceptron, or kind of like the building block of a deep neural network, this equation right here is what we call a fully connected or linear layer. And the reason we call this a linear layer is that it is just linear operations, right? We do a single matrix vector multiplication, and then we add on a single vector. So there are no quadratics, there are no square roots, it's just linear. Okay, and actually with this linear layer, we have everything that we need to kind of understand this multilayer perceptron. Well, almost, but very close. So now let's think about the output real quick. So in the output layer, we have, and let's call this y, or let's call this y hat, as we did earlier, because this will be the output of the model. So this we will call y hat 1, this we will call y hat 2, and this we will call y hat 3. Sorry, the colors are bad. I should use a different color for that. It's all good. Okay, so y hat 1, 2, and 3 should have the same relationship to the h's that the h's had to the x's, right? Because this is just another linear layer. So in other words, let's let, you know what? Let's copy this and drag it down so that we still have the picture, but not all the clutter around it. So we're going to copy, and then we are going to paste here. Okay, excellent. Okay, cool. So so here we see that y hat 1, similarly to before, should equal some function of h11, h12, h13, and h14. So again, this will be some function of h11 all the way to h14. Okay, and in particular, that function will be, again, just the thing with the weights. So here, technically, all of these weights should have a 1 over them because this is the first weight matrix. And now we're about to do the second weight matrix. So I'm really sorry. Please bear with me in all the indices and notation. But the TLDR is that y hat 1 equals W211 H1 plus W212 H2 plus W213 H3 plus W214 H4, and then plus, let's call this bias. I forgot the script on the bias. Let's call this B21 here. Sorry, these are not squared terms. They are just superscripts which indicate which layer we're in. So that's what all the 2's mean. Okay. Yes, I can share these notes afterwards. That is totally fine. Yes, I got you. Okay. Cool. Okay, so again, if we look at this as the matrix vector product, it'll be very similar, right? So we have y1 here, we have y2, which equals a very similar thing. We have y3, which equals a very similar thing. And so again, if we take all of these weights and we arrange this into the weight matrix, and then we pull out all of the h's, and then we arrange, sorry, that's not right, and then we arrange the h's into a vector, then again, we have this matrix vector product. So in particular, similarly to last time, let us call this weight matrix W2, and then let's call the h's just H1, and let's call the bias, in this case, B2, since, yeah, it's the second layer of bias. Okay, excellent. So in particular, then our succinct linear equation here looks like y hat in general equals W2 times H1 plus B2. And so this is kind of like the final, so this is kind of like the final sort of like equation that we're going to be looking at. Okay, and now finally we have all the building blocks we need, asterisk, not really, but very close to understanding this entire model. So first off, let's just start from the end and work backwards, right? Since we're in GKR land and that's what we do. Okay, to check that I follow, y hat 2 is the probability of the output being y2. Yes, that is the perfect way to interpret this if this is a classification problem. Yeah, so in general, your outputs will look something like 0.3, 0.5, 0.2, and then you can see y2 as exactly the probability of that. Yes, excellent. Okay, cool. So again, now let's look at this entire function. So what is y hat as a function of x, right? Because that's what we really want to know. Well, y hat already equals W2 times H1 plus B2. That's great, but that's still not in terms of x. So we need to expand H1 a little bit. We know that H1 equals W1x plus B1. And now we have the final form factor. So to write it all out, we have that y hat equals W2 times W1x plus B1 plus B2. And so you can see here almost like the recursive nature, or kind of like the layered nature, right, of a multi-layer perceptron, in that every single layer that we add on, we're just going to, let's say we had a W3, right? Well, we're just going to multiply W3 to this entire outer thing, and then we're just going to add B3 to this. and so on and so forth. And so this formula, this whole thing ends up being, sorry, I know we're drawing a lot of boxes and saying, oh, this is the end all be all. This formula is almost the end all be all for a multi-layer perceptron. So MLP star, not really. Okay. Okay, what questions do folks have about this component? This is very important to understand because we're going to do a thing that relies on this understanding. Okay. All right. Okay. Excellent. Okay, perfect. Okay, so there is one problem with this. There is an issue which is kind of inherent to all of this stuff. I would force y'all to think about it, but I feel like that might be a little mean. So I'm just going to tell y'all what it is, which is that let's write out this formula again. Y hat equals W2 W1x plus B1 times, this is B1 plus B2. Okay, there is a problem. And the problem is that this model is bad. And it's bad because it's actually no better than a one-layer model. And in fact, no matter how many W3s, B3s, W4s, B4s, so on and so forth that you add, it's never going to be any better. And the reason is very simple, which is that the whole model is linear, right? In other words, if I distribute W2 into this block right here, we have that Y hat equals W2 times W1 x plus W2 times B1 plus B2. Well, this thing is just a vector, and this thing is just a vector. So we can actually just combine these into one vector. Let's call this B star. Also, W2 times W1 is just a matrix. We can combine these into a single matrix. Let's call this W star. In other words, Y hat, despite all the work that we did to have these like different layers and make things all fancy, Y hat at the end of the day is just W star x plus B star. It is still a linear classifier, which is not what we want. Okay, so that's not great. And the question is, how do we resolve this, right? How do we make it so that the layers are actually meaningful and actually do something as opposed to just all collapse on each other? And this is where the final kind of like insight of deep learning comes in, which is that between layers, we need to add nonlinearities. So what is a nonlinearity? Well, it's just a function which isn't a linear function, basically. Maybe let's get some examples of nonlinearities, right? So a couple common examples, like the early examples of nonlinearities, question mark. So some common examples are, for example, the sigmoid nonlinearity. Actually, let's start easier. Let's start with ReLU. ReLU stands for rectified linear unit. As you might have guessed, it is almost linear, but not quite, which turns out to be enough for neural nets once you stack enough of these together. ReLU is an element-wise operation, which means that when you, which means that when you compute ReLU on X for a vector, well, let's define it for a scalar first. So let's say that X is just a real number. So in this case, ReLU X is just going to be the max of 0, X. And in particular, the graph looks like, well, when we're negative, we're going to be 0. And then as soon as we hit 0, we're linear. So this is ReLU. Okay, and ReLU for a vector is exactly the same thing. So in other words, when we apply ReLU over X arrow, where X arrow is in RK, for example, this is just going to be the vector ReLU of X1 all the way to ReLU of XK. So in other words, you just apply element-wise to everything in the vector. Okay, so this is one example of a nonlinearity. And we like ReLU because ReLU is mostly linear except where it's not. And what this means is that it's great for gradient descent, but again, we won't talk about that right now. Another nonlinearity is what we call the sigmoid nonlinearity. So the formula is a little bit trickier, but sigmoid, similarly to ReLU, is a element-wise function. So once we define it for a real number, it's easy to define it for a vector or even a matrix if you would like. But sigmoid of X is just going to be equal to 1 over 1 plus e to the minus X. This looks kind of weird, but the graph is actually really pretty. And in particular, the graph looks something like this. So when you're really, really negative, you're really small. And then once you get here, you get very close, and then you kind of asymptote again. And the two asymptotes of this function are going to be y equals 1 and y equals 0. In particular, you can see that if x is really, really, really small, then e to the minus x, where x is a really large negative number, this will be huge. So then 1 over 1 plus something which is huge is e to something which is huge, which is going to be something which is huge, is tiny because it's 1 over a huge number. Similarly, when x is really, really big, e to the minus x is close to 0. And so this whole thing becomes close to 1 divided by 1, which is just going to be 1. Let's see, been a while, but why do we fundamentally need nonlinearities? Kind of forgot. Yes, great question, Noah. So this is exactly the collapse phenomena that I was talking about earlier, right? So if we don't have nonlinearities, in other words, if we don't have these things between the layers, right, and we just kept on adding W1, we add W2, we add B2, we add B3, we add W3, so on and so forth, unfortunately, the linearity of all the operations means that we can just distribute W2, for example, into the parentheses here, and we can receive W2 times W1 becomes another, sorry, I should highlight this, but yes, we can distribute basically W2 into the parentheses, and that will give us this W2 W1 times X, and we can just call this W star, right? And so unfortunately, no matter how many W's you add, they all get accumulated in here, and then we just have W star. And at the end of the day, our model is just this, which is bad. This is not what we want. We want a very complicated model, and this is a very simple linear model. So that is fundamentally why nonlinearities are important. Okay, cool. Any other questions? Okay, awesome. Okay, I'm doing a wavy dance to make you all feel good about asking questions. I don't know how this is helpful. Okay, all right, cool. Then we're moving on. Okay, so now that we have nonlinearities, finally the question is, where should we place the nonlinearities? And the answer is, well, it's very straightforward. We just place them in between each layer. So let's pretend, for example, that we're going to just use ReLU in this case. So if we take a look at our earlier model, well, we have y hat equals W2 times the output of the first layer. Why don't we stick a nonlinearity there? Why don't we just stick a ReLU right here? Question mark. And the answer is, we should. That is what we should do. Okay. So in other words, to stop this collapse thing from happening, we have y hat equals W2 times ReLU of this whole thing, W1x plus B1 plus B2. And now, is it to stop the layers collapsing into a linear equation? Yes, that is exactly correct, Hen. That is the whole point of the nonlinearities, because otherwise, as mentioned earlier, if we do not have this ReLU here, then we could immediately distribute the W2 inside the parentheses, and then we would get full linearity, and everything would be over and would be very sad. So that is why we have the ReLU. All right, cool. So to recap, what did we learn about? Oh, we learned that Ryan cannot erase things, but that's okay. So to recap, basically in a deep learning model, generally speaking, you will have a linear layer or something similar, followed by generally a nonlinearity that stops the layers from collapsing together. And in this way, if you layer enough basically layers on top of each other, you will be able to learn very, very complex functions, very complicated relationships, so on and so forth. Okay, so that is the kind of end of the deep learning segment part thingy. Okay, awesome. Okay. Cool. Okay, sorry, I'm aware that we are running low on time, but that is okay, because we will speed through the GKR section because y'all are already GKR experts, because Yupeng is a GKR expert and he taught y'all well. Okay, excellent. Okay, so part 3, why zkML and GKR? Or actually, oh wow, we did not talk about zkML. Holy cow, okay, wow, we are so behind. I am so sorry. Okay, wow, okay. Quick, time to talk about zkML. Please slow me or stop me if you have any questions, but otherwise we're going to speed through this. Okay, so what is zkML? Well, generally speaking, zk allows you to prove that a particular circuit or a particular program was executed correctly, right? So if I have, this circuit, this like GKR circuit, and I am like multiplying here and I'm adding here, then let's do another thing here. Then GKR allows me to, or zk rather allows me to prove that some claimed output y here equals the correct function of the x's here. So that is in essence what zk allows us to do. And zkML is basically just an application of that to machine learning. So if we revisit the thing that we had earlier, which is f of x comma theta final equals y hat, what we are doing in zkML is proving that when you run x or f, which is fixed, and theta final, which is fixed, on x, which is a thing that's given to you, then the output that you get is actually y hat and not some other y hat prime, which is malicious, right? So in other words, we're trying to show basically that the person who is running the machine learning model did so in the correct manner. They did so such that the model was, or they did so with model integrity, quote unquote. So they didn't, for example, replace theta final with theta final prime, which doesn't equal theta final, and therefore got a different result than theta final. Cool. Okay. So yeah, so TLDR behind zkML is that during inference time, we want to prove that the model was run correctly using the correct parameters on the correct input. And that will give us the correct result, of course. And so that is the process that we are proving the correctness of. Additionally, because of the ZK feature of basically zero knowledge proof systems, it is possible to hide certain things. So in particular, in this case, we might say that theta final is the intellectual property of whoever trained the model, right? Like if you just went out and spent hundreds of thousands of dollars or millions of dollars training this latest and greatest language model, you might not want people to know the model weights, or maybe you want to open source because other reasons, but like maybe let's say you're a proprietary model and don't want people to know the model weights, but you still want everyone to know that you trained the model correctly. So in that case, what you would do is you would take something that we call a polynomial commitment scheme, or PCS. I know that there was I think lattice fold talk previously. So lattice fold, for example, is one example of a polynomial commitment scheme. But the point is that you take the values in theta final and you run a PCS over theta final, or rather PCS commit over theta final. And then this you will send to a trusted third party, such as the blockchain, for example. So you'll post this commitment on chain. So this commitment will go to on chain. And then later, when you're trying to show that this inference process happened correctly, you will generate a proof. So you'll generate a snark for this particular circuit, which represents the machine learning model. So during the proving process, you will have something like pi, comma, x, comma, y hat. And so this tuple is another thing that you'll send on chain. And so basically what the on-chain verifier should do is it should verify that pi, which is the proof for specifically f, and theta final, along with the input x and the output y, is the correct execution of the function f, or of the machine learning model in this case. And so in essence, the commitment that you basically put on chain earlier to the weights, even though it is hiding and therefore doesn't reveal anything about the model weights, should allow you to verify that the model was run with the correct weights on the given input x, which gives you the output y. Okay. That was a very, very fast kind of overview of zkML and what it is and how it works. What questions do y'all have? Thank you, Katya. That is very nice. Okay, love it. Okay, all right. Okay, cool. Okay, so excellent. Okay, sounds like y'all got it. Okay, great. Okay, then we are moving on to part 3, which is GKR, question mark? Okay, so now the question is, okay, there are all these proof systems. There is Hyperplonk. There is Spartan. There is, oh my God, I'm losing my mind. There's Groth 16. Like there are all these proof systems out there, right? There's all the folding schemes like Nova, Hypernova, Supernova, whatever, Protogalaxy, all these things. Cool. Okay. Why GKR, right? Like, why are we doing this thing for machine learning? Well, the first reason is actually that in GKR, so as you'll have learned with Yupeng, in GKR, you have a layered arithmetic circuit, right? And this layered arithmetic circuit probably looks pretty similar to the diagram that we just drew, where you have a bunch of gates. And the idea is that you take the various basically layers within GKR, within the GKR circuit, and then you compute basically operations on them to derive the next layer. And so really, really quickly, what happens in GKR, right, at a very high level, is that you have this output, and let's call this output v tilde0 of x1. The reason, are y'all familiar with multilinear polynomials? I assume that Yupeng talked about this. Just a quick yes, no type thing. A little bit. Okay, Cool. Okay. Okay. So yeah. Okay. Then let me review multilinear polynomials super quickly. So the idea of a multilinear polynomial is that it basically encodes a vector. So it is kind of like the polynomial extension of a vector. In this case, let's say that, for example, this vector right here has two elements, right? And let's say that the values are 3 and 7. So if we wanted to encode this vector, then one way that we can do this is to say, let's index this vector in a binary fashion. So 3 and 7 are the values in this vector, but maybe let's call this first value 0, and let's call this second value 1. So in other words, when I plug in 0 or 1 to v0, then I should receive either 3 or 7 respectively, right? And there is a nice polynomial way to do this, and the idea is as follows. So v0 tilde of x1, so if x1 is 0, in other words, if 1 minus x1 equals 1, then we should output 3. And otherwise, if x1 equals 1, then we should output 7. So this will be kind of the polynomial formula for this particular multilinear extension. And the reason it's called a multilinear extension is that, let me just write out the word, multilinear extension. So this is also known as an MLE. But the reason that it's called a multilinear extension is that, first off, it is linear in x1, right? So in other words, x1 is always a degree 1 variable. And the reason it's called an extension is that when you evaluate it at 0 or 1, or when you evaluate it at 0, this will be 0, this will be 0, therefore only this term survives, therefore you get a 3. And when you evaluate it at 1, let's do this with a different color. When you do it at 1 here, 1 minus 1 is 0, so this term cancels, and now only this term survives, so then you get 7. So in other words, when evaluated over what we call the Boolean hypercube, or basically all of the binary kind of like values, we get the original vector back, we get the original values back. However, we can evaluate it at the number 2, for example. So if we evaluate it at 2, then we get 1 minus 2, which is negative 1 times 3. So we get negative 3 plus 2 times 7, which is 14. So evaluated at 2, this will give us 11. And so it turns out that we can just evaluate these functions anywhere, basically over R, in this case, finite field, as opposed to the reals. You can also evaluate over the reals, but for cryptography, we want finite fields. And the point is that basically, we're extending this vector, right? So if we change any value in this vector, let's say we change this 3 to a 4, well, now everything changes, right? Because this 11 is no longer an 11, this will become a 10, right? And I assure you that if we evaluated it at more points, let's take 3, for example, originally it would be negative 2 times 3, which is minus 6, plus 3 times 7, which is 21. So it would be negative 6 plus 21, which will be 15. So originally, the OG is 15, but then if we change it to 4, the new will be, let's see, negative 2 times 4 plus 21, which will be 13. Right, so if you alter any of the values in the original vector, the entire polynomial changes, and that is why it is the polynomial encoding of such a vector. Okay, that was probably more about MLEs than you wanted to know, but good to know it anyway. Okay, excellent. Okay, so in GKR, what happens? Well, the prover in this case is going to claim that the multilinear extension of the output should be this 3, 7 polynomial. And the verifier says, well, obviously I don't believe you, right? So the prover and verifier are going to engage in this game where the relationship between two layers, canonically at least in canonic GKR, looks something like v0 tilde of, I'm going to call this x1, should equal the sum of x comma y, where each of x comma y, and wow, this circuit has 5 elements in it. Let's make it 8 elements, so we're the next power of 2. But the point is that x, y should be in 0, 1 each to the 3, because we need 3 binary variables to represent 8 elements, right? And then the idea here is we're going to have add tilde I plus 1, or I guess in this case just 1, add tilde 1 of x1, xy times vi plus 1, again, sorry, this is just v1, so sorry, of x plus v1 of y, plus mol tilde 1 of, again, x1, xy of v1x times v1y. Okay, this equation should look familiar from Yu Peng's talk. But the TLDR is that it basically relates all of the values in the current layer, which is v0, to values in an earlier layer, which is v1 here. And so the whole idea of GKR is that you're going to do Sumcheck over this expression, right? So you're going to do Sumcheck, you're going to bind x to, let's say, u in F3, and we're going to bind y during Sumcheck to, let's say, v in F3. And at the end, we're going to receive these claims on the multilinear extension of the previous layer. So we're going to want to know that v1 of u, for example, equals question mark, say C1, and that v1 of v equals question mark C2. And so these will be the Sumcheck claims that we need to prove as the prover for the next layer. And so this is the TLDR behind how GKR works. Any questions real quick? Okay, cool. Okay, the crickets are chirping, I see. Okay, all right. Okay, then maybe the last thing that I will talk about then is why GKR is really good for neural nets versus a different proof system. And actually, it specifically has to do with matrix multiplication. So what do I mean by that? Okay, so in neural networks, as we pointed out earlier, there is this idea, right? Like the final formula for this neural network, sorry, if I can find it, looks like this, right? It's y hat equals w2 times this thing, which by the way is just a vector, plus b2, which is a vector. So always in these neural nets, you have these giant matrix vector multiplications, which are just matrix multiplications where the second matrix is a vector. And so we're going to take a look very, very quickly at how to do a matrix multiplication using Sumcheck, which is something that you can then use in GKR. Okay, so for the final part of this, also, I think we might go over by 5 minutes. If you need to hop, please feel free to hop. Otherwise, I will stay on for a little longer and try to explain the map-mult Sumcheck thing in depth. So let's do it. Okay, so the final part of this talk, part 3, 4, I have no idea. Let's call it part 4. Mat mult plus Sumcheck. Okay, excellent. So what are we doing here? Well, we're trying to check in general that a matrix C equals question mark the product of matrices A and B. And let's define this a little more rigorously. So let's say that A is a M by N matrix, and let's say that B is a N by K matrix. So that means that C, in this case, needs to be an M by K matrix. Also, as a general rule of thumb, whenever you're multiplying matrices, the center kind of dimensions need to match, and then they also just cancel out. So the final matrix is always the first dimension of the first matrix by the second dimensions of the second matrix. So that is how I was able to compute that. Yeah, okay. So let's just draw this out, right? Let's say that A in this case is this. So A is going to be M by N. B in this case is going to be, let's say like this. So this should be N. That doesn't look right. Let's make it like this. Okay, so B in this case is N by K. And then this equals question mark C, which is going to be M by K, where K is quite skinny. Okay. And then the way that matrix multiplication typically works is that you iterate first. So if we were to just write this in code, we would say something like for row in A. So in other words, we're going to iterate through all the rows of the first matrix. Let's make this pink so that it's color consistent. And let's also make this pink so that it's color consistent. But yes, so for row in A, and then we're going to say for column in B, right? So we're going to multiply by all these columns. We're going to say that C bracket row bracket col equals row transpose times col, where row and col are each just where row and col are the respective vectors. I guess you don't need to transpose the row. Yeah, so this should just equal row dot col. So in other words, this first entry of C right here should equal the dot product of the first row of A with the first column of B. Okay, cool. So this algorithm, we basically want to encode, in some sense, into the Sumcheck formula. So rather than just having C, A, and B, let's define C tilde, A tilde, and B tilde. In other words, let's define the multilinear extensions of these matrices. So in this case, C tilde, which should be an extension of C, this is going to be in, well, okay, so the question is, how should we actually think about C tilde? Well, maybe we should still think about it as a matrix, right? Because that is kind of the intuitive thing to do. And actually, we're going to change this to A tilde because that will be easier. So again, A tilde is M by N. So if we wanted to find an arbitrary entry in A tilde, how would we do that? Well, we could do it by maybe indexing first which row it is. So maybe we would do something like A bracket row bracket call, right? So we might look down and look for which row it is. So it's going to be this row. And then we might look right. And then we might say, oh, it's this column. And in particular, let's make these binary. So the row is going to be the binary decomposition of the row index that value is in. So for example, if the row is 5, then let's make this more concrete. So if this point, that was the eraser. Okay, so if this point right here is, say, the 5th row and the 21st column, that I don't want to do the binary decomposition of 21. Let's say it's the 9th column. Then the row here should be 1, 0, 1, which is going to be 4 plus 0 plus 1, which is 5. And the column here is going to be 1, 0, 0, 1, which is 8 plus 1, which is 9. Okay, so this is how we're going to get our multilinear extension. So we're going to use the kind of same formula as previously. And in this case, A tilde is going to be a function from f log m plus log n to f. In other words, we started with basically these two binary strings, right? And the question is, well, what is the length of this? Well, the length of this is just going to be log m, because there's m total possible indices, and the bit string that can represent basically m things is log m. Oh, am I being kicked out of this room? Oh, okay. Sorry, folks. Give me 1 second. I might be getting kicked out of this room. Yep, I'm being kicked out of the room. Okay, I'm so sorry. I'm going to mute myself. Oh, okay. Sorry, how do I? Okay. All right, give me 1 sec.
I was going to jump on stage while Ryan's getting set up again and just remind
Sorry. Damn.
Don't worry, Ryan, it's absolutely fine. From the chat, it looks like everyone is really enjoying your session so far, so no sweat.
Okay.
I wanted to jump in and remind people that if you've missed any of the live workshops, they're all recorded and they're all posted on the Encode Club YouTube channel, and you can find them in the hashtag. So definitely do check them out if you've missed any. And if you particularly enjoyed this session from Ryan, but you think you want to go back and review anything, then the recording will be posted tomorrow, and you can definitely do that. Okay, I'll hand back over to Ryan.
Okay, no worries. Yes, and I will also send Rebecca the lecture or the notes, I guess, from this if you want to see the really messy handwriting. So yeah, yeah, please feel free to do that. But okay, let me reshare and we will do this Sumcheck map mold stuff. So y'all get ready. It's gonna be good. Okay. Oh, am I not screen sharing anymore? Whoops. One moment. We'll be sharing screen. Okay. All right, excellent. Okay. Okay, I don't have the other laptop anymore, so I won't be able to see. So Rebecca, I might need your help to yeah, maybe I can just like scroll over and stare at the chat. Okay. All right, okay, cool. Welcome back, everyone. Okay, welcome back. Yes, we were talking about basically indexing this matrix with binary values, right? And so again, A tilde in this case, or even if you were to just index into the original matrix A with, I guess, like with binary values, well, if there are m rows, then you would use, in general, log base 2 of m binary indices to index into the rows. And then if there are n columns, similarly, you're going to use log base 2 of n binary indices to index into the columns. And in general, when we take the multilinear extension of all of this, then we can plug in not just binary values, but actually field elements. And that is why it is f log m plus log n to f. So the function basically looks like that. And what this means is that a tilde in general will take in what I'm going to call, let's see, let's do, okay, this is tricky, x, y, and z. Yes, let's do that. So a of x comma y, where x is in f to the log m, and y is in f to the log n. This is going to be the final form factor, basically, of this multilinear extension. And the way that basically the actual formula looks, if you're interested, is very similar to the multilinear extension that we had earlier. So in this case, let's say that, okay, yeah, let's break down this a little further because it's so easy to write shorthand, but we don't want to do that. So in this case, it'll be x1 through x log m, comma, y1 through y log n. And this should equal basically 1 minus x1 times 1 minus x2 times all the way to 1 minus x log m times 1 minus y1 times 1 minus y2 all the way through 1 minus y log n. Okay. And then finally, it'll be all of this times the very first value in A. So let's just call this times A11 plus, and then a very, very, very similar formula, except now the last coordinate is just y log n times A12, where A12 is going to be the second value in this matrix, plus so on and so forth. So this is kind of the formula or the form factor for A tilde. Let me see, are there questions? Okay, sorry. Sorry, you'll have to see the infinite mirror over and over again as I try and look at the questions. Okay, but yes, okay, so this is the form factor for basically that particular multilinear extension. And again, the reasoning for this is very straightforward, right? Which is that A11, well, what is the index of A11? Well, the row is just going to be 0, 0, 0, and the column is going to be also 0, 0, 0, 0. So if all of our variables are 0, then if we plug in 0 here, 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 so on and so forth, then all of these values will become 1. And once all these values become 1, the only term that survives is the A11 term at the end. And in every single other thing that is coming, there will be at least one variable which stands on its own. For example, y sub log n will be 0. And so the A12 term won't contribute anything to the sum, and therefore the final thing will be A11. So again, similar kind of like multilinear extension type stuff, except we're now just reinterpreting the multilinear extension in 2 dimensions as opposed to 1 dimension. Okay, so that is how we interpret a matrix into a multilinear extension. What questions do folks have at the moment? I'm so sorry. Oh my God, the infinite mirror is terrible. I'm so sorry. We'll give it a couple seconds. Okay, 3, 2, One? Okay, no questions. Excellent. We're going back. All right. So, okay. So the final step of all this is, okay, great. So now we have our multilinear extensions of such things. How can we do Sumcheck over this? And the formula, as you'll see, will be very, very, very similar to that of the matrix multiplication formula. So in general, let's say that C tilde of Z1 through, sorry, let me use the right colors this time. So I think C was green. So C tilde of, let's see, x1 through x log m. And again, the reason for this is that, as a reminder, C is a matrix in F m by k. So to index C, we first need log m variables, and then we need z1 through z log k. So now we need log k variables to fully index C. So we want to show that, oh, I'm so sorry. Okay, yeah, so we want to show that basically this thing equals the sum over y1 through y log n in 0, 1 to the log n. So we want to show that this equals the sum over all of the middle variables, right? I guess just me, maybe let's start by reviewing the canonic matrix multiplication setup. So in this case, B is going to be in F n by k, and then A is going to be in F n m by n. Okay, so canonically, if we were to ask, okay, well, what is C at basically some row, comma, some call, right? Or let's call this C at x, comma, z, where x and z are indices. So what does this equal? Well, this should equal the sum, the sum over y in basically, let's say y goes from 1 all the way to n in this case. And the idea here is that we're going to sum over a of x comma y times b of y comma z. And so pictorially, what that looks like is exactly what we had earlier, right? So in this case, x is going to be the row, z is going to be the column, and then y is going to be the iterated variable that sums over this entire row in the first case, or the entire column in the second case. So that is why the formula looks the way that it does, right? So we have axy, where y is iterated, times byz, where y is iterated again. Okay, so now we will try to extrapolate this into the multilinear setting. So very similarly to the above, instead of x and z being decimal indices, we now have the variables x1 through x log m, which are binary indices, and z1 through z log k, which are also binary indices. And in this case, these should equal the sum over y1 through y log n, which are going to be binary indices. And in this case, we will do something very similar, which is we will evaluate the multilinear extension A at x1 through x log m, comma, y1 through y log n, times the multilinear extension of B, sorry, I'm out of room here, evaluated at y1 through y log n, comma, z1 through z log k. So these two formulas should look very, very similar because they actually represent the exact same thing. It's just that in the above, we are indexing everything in decimal notation, and in the below, we're indexing everything in binary notation. What question do folks have at this moment? Going back to the infinite mirror. Okay, I'm looking. Okay, we're gonna go back in 15 seconds. Okay, Simon, that makes a ton of sense. Yeah, this is a lot of like math and polynomials that are being thrown at you right now. So no worries, that makes a ton of sense. Okay, but let us carry on and then we will try and wrap this up. Okay, so as stated earlier, C of xz, so we're trying to check basically that for a single output, x comma z, right? So in this case, in the above case, this dot right here is C of xz because it's a single value or a single entry in the C matrix. So we're trying to check whether this equals this row here in the first matrix times the column in the second matrix, right? As in, that is exactly what this formula is trying to show us. But it's not good enough to check a single entry. In fact, we need to check this for all the entries. So in particular, we want to check for all x1 through x. Oh, we're not going to have enough room for this. Okay, let's draw an arrow here to make things easier, but we don't want to just check this relationship for a single thing. We want to check that for all x1 through x log m in 0, 1 to the log m, and also, log m, and also for all z1 through z log k in 0, 1 to the log k. So we want to check for both of these, or for all of these, that this relationship holds. And so here, instead of literally manually checking this for everything, this is where our good friend Schwartz-Zippel comes in, and here is where we can make use of the fact that multilinear extensions can be evaluated at non-binary values, right? So if we were canonically indexing into C, all of the x's, all of these guys would need to be in 0, 1. Like these would all have to be binary for the matrix to semantically make sense in some way, right? But it's no longer a matrix. It is the polynomial extension of a matrix, which means that we can evaluate these anywhere. And so in particular, this check, this for all check, this is roughly equivalent, sans basically 1 over f, I think. Yeah, I think it's just going to be 1 over f. Oh, maybe it's like 2 over f. But the point is that this is almost equivalent, except for probability 2 over f, as the check, is it true that C tilde at, let's call this UVW, that works. Okay, so let's call this, no, let's do G1, yeah. So is it true that C tilde at G1 through, no, we're going to use U and W actually, sorry everyone, at U1 through U log M, comma, W1 through W log K, is it true that this, so what we're doing here is we're actually plugging in, all of these are going to be random field elements, so they're no longer binary, right? So we're plugging in field elements in F log M, and these are, again, going to be field elements in F log K. And so the question is, if we plug in random field elements, effectively, we're kind of taking a random linear combination of the whole matrix here, but is it true that this equals, question mark, the summation over still y in this case from earlier. So this is going to be y1 through y log n in 0, 1 to the log n. But the question is it true that this should equal still the summation of y1 through y log n of, again, evaluating exactly those multilinear extensions. So in this case, A tilde will be evaluated not at x, but at the u's. So u1 through u log m, comma, y1 through y log n times, and again, we're going to do b, but b is also going to be evaluated at the w's rather than the u's, or sorry, the w's rather than the z's, where the z's are binary, if you recall, and the w's are field elements. So here we have b from of y1 through y log n, comma, and now it's going to be w1 through w log k. So this will be the new check that we're doing. And because this check is basically equivalent to checking that all of the entries in C match all of the things here, we're basically good to go. And the final thing to do is to basically run Sumcheck over this thing right here. And y'all know how to do Sumcheck, thanks to Yuping. So that should be all good. Okay, what questions do folks have? Find me, Ryan. I can only hear your voice right now. I can see the screen. Okay, excellent. Okay, let me stop screen sharing. Okay, cool. Okay, yes, sorry. That last section was very kind of rushed and definitely a lot of math and background and intuition needed. thank you all so much for coming. Otherwise, are there any final questions or comments that folks wanted to chat about?
I think we have a few people typing in chat, but I think I can speak for them all when I say that was an absolutely brilliant class, Ryan. Thank you so much for joining us and giving us that session. For anyone who did get a bit lost, I think someone mentioned it earlier, you can absolutely just rewatch the video. You can take notes yourself, and Ryan will share the notes with us as well, so you'll have access to them as well.
Yeah.
Let's see if these people typing have questions or if they're just going to thank you. Nu has asked if you have any paper recommendations to understand the maths behind this, like some classics to understand it.
Yes, I do. So there is this lovely, lovely textbook called Proofs, Args, and ZK. I will drop the link in the chat right now. This is by Justin Thaler. Yes, exactly. Justin Thaler also has a little note on GKR, I think. Is it this? Sumcheck Thaler. Yeah, he has, oh, here it is. Yeah, a note on the GKR protocol. Excellent. Okay, so this is another nice one to look at. It's like it's like a shorter kind of like version of chapter 4 in Proofs, Args, and ZK, if you just want to get the overview. And then one of the really nice papers, which was actually published by, I think, at least one of the polyhedra, oh, is that true? Okay, there is this paper called zkCNN, which was published a while back. I don't think any of these people are affiliated with polyhedra, but they're good friends with the polyhedra folks, and they're very, very smart. And this paper is really cool, but I would only recommend this after you've gotten Sumcheck. Recommendation: pre-transformers world and the current transformers world. I think so. So I think 3 Blue 1 Brown has this really, really, really good lecture series on neural networks into transformers. He doesn't cover any of the like recurrent networks or vision networks or things like that, but he does an amazing job on transformers. So highly recommend 3 Blue 1 Brown transformers. Yes, it should be this. And the first 4 parts of the series are also huge if you want to get more intuition for neural networks and backprop and stuff. But yeah, that would be a good place to start. And I think there's tons of like tutorials, or Coursera should also be pretty good for this. Yeah.
I love that 3 Blue 1 Brown series. Is so well explained.
Yeah.
And if you're interested, if you like 3 Blue 1 Brown, he does a really cool video on how he makes his graphics, especially for the LLM video. It's really impressive. He's got his own software. It's crazy. I love it. Okay, awesome. Do we have any other last minute questions for Ryan? I know we've overrun a bit, but I'm super impressed to see how many of you have stuck around to see it through to the end. Any last minute questions? Otherwise, we'll wrap up for today. Nu is typing.
It's just really fun. Like, I don't know, like the math is really cool, and yeah, like you just kind of get excited about it. I mean, it's crazy like what AI has managed to do recently. Like back in my day, not to sound old, back in my day, it was like, here's this really, really specific data set, and you're going to work for months and months and like barely beat state of the art on it because you like way overfit to it or something like that. And now it's like, ChatGPT beats every benchmark everywhere. Now there's like DeepSeek or whatever, which again beats every benchmark everywhere. Yeah, it's just really crazy how powerful things have gotten, and yeah, it's very exciting.
Yeah, Nu enjoyed your personal style. Thanks a ton. Yeah, okay, amazing. I have a feeling that all the rest of the comments now are just going to be about what a good teacher Ryan has been, and just lots of thanks. So we'll end here for today. Thank you everyone for joining us again for another Explore Expander Bootcamp workshop. We will see you all tomorrow for the next one. Bye everyone.
Thanks, Rebecca. Take care.